Object A with a mass of 3 kilograms moving at 8.1 meters per second bumps into the back of Object B with a mass of 2 kilograms moving more slowly in the same direction at 4.5 meters per second. If the collision is completely elastic, what are the speeds of the two objects after the collision? Okay, so we did a problem similar to this in class, but anyway, let's get into it. We're looking for the speeds of the two objects after the collision, and we're given some data. First of all, let's take down the masses and velocities. Okay, so you have a mass of, and this is all already in standard units. So the first object we're going to note as M1 has 3.0 kilo. I'll just write 3 kilograms. Second object, or the first velocity, is 8.1 meters per second. Again, already in SIs. Then your second object, okay, let's see if this can fit in there, has a mass of 2 kilograms and a velocity of, well, these are initial velocities, so an initial velocity of 4.5 meters per second. Okay, so we have this data. We also have a very important piece of information we need. This collision is completely elastic. What does this mean? This means that the kinetic energy is conserved, which means no energy. It's not neither of the objects are deformed, and no energy is wasted. It's just one object hits another, and all the energy is transformed. So this would be like if this were in a real life scenario, you could think about a pool table, and you could, or a game of billiards, which are the same thing. Well, not exactly, but they're very similar. So just the cue ball hitting any of the other balls, it's just the energy is transferred. So if it's completely elastic, right, so we're looking for the final velocities. So we're going to set up our form, since it's an elastic collision, that means our coefficient of restitution, fancy word for fancy phrase, or E, which is the coefficient for the it is the coefficient of restitution, E, which equals V2 minus V1 over, okay, what I'm saying here is the coefficient of restitution is equal to the second final velocity minus the first final velocity over the first initial velocity minus the second initial velocity. It's kind of a mouthful. I would more look at it and take the image of this or the actual formula than try to understand the wording, because it's not really that hard. It's just you switch these, and it's after over before. It's not, yeah, it's not a big deal. And since it's elastic, this whole thing equals 1. That means, again, the velocity. That means there's no change. There's no loss of energy. So let's see. This is actually step 2. Another important formula we're gonna go by. Well, I don't know if it's really a formula. Okay, I'll write it here anyway. P1 plus P2. So the initial momentums are equal to the final momentums, and this is always the case in any collision, unless there's a change in impulse, which means there would not be a conservation of momentum. So yeah, that's what we've shown here. We've shown the formula for the coefficient of restitution, and we've shown the formula for the conservation of momentum. So those are the two things we're going to use to solve this problem. Okay, so let's then, oh, and also let's draw a diagram. So actually I could pair that up with this, but I won't because time. So you have your first object, and you have your second object. Okay, this might be a squeeze. I'll go ahead and use the erase tool. I'll just use, okay, okay, there it is. Let's just go ahead and so you have your M1 here, right? You have M1. We'll just say P1 actually, because this is just the whole object, and we're just kind of showing its momentum through its mass and velocity. So this is its mass, this is its velocity. Okay, then you have equals P1 after P1 prime. Again, the prime denotes that it's the after, the post crash or whatever. And so we know for sure this is moving in to the right, because, or in that same, it's not changing directions, and we know that because the first object is hitting it in that direction. So it would just be illogical for it to change directions when it's only increasing velocity. However, we don't know the direction of this. We will find out. If it's positive, it goes in the same direction. Negative, it goes in the opposite direction. Okay. Oh, and I forgot the prime. Okay, so that's our diagram. Now let's get to the actual grid of it. Let's do the work. And I'll actually switch to the text tool because, well, you might see why it's annoying, but it's a lot less annoying than my handwriting. Okay, so first of all, actually, before I do that, let me just show something. So no typing tool just yet. Okay. So with this formula, what I'm going to do is multiply both sides by v1 minus v2. So you have v2 prime minus v1 prime equals v1 minus v2. And you can't really do this exact, well, you can use the same process, but you won't get the same answer if the coefficient of restitution isn't 1. Let's say it's 0.5. Let's say the coefficient here is 0.5, then this would be v1 minus v2 times 0.5. But in this case, it's not. It is 1. So, you have all this, now let's switch to the text tool. Yay, okay. So, we're going to get started with the actual calculations. So first we're going to do the calculations for the momentums. Mass 1 times the velocity 1 is 3 times, yeah, that'll have to do 8.1. So the first momentum plus the second, and these are initial momentum, so the first initial momentum plus the second initial momentum equals the first final momentum, which is, we know that the mass is the same, so wait, let me just, see, this is what is kind of annoying, yeah, so then, I'll draw that in a second, plus the second velocity, or momentum, final momentum. So let me just draw something in here. Actually, let me just, give me 1 second, fix it a bit. Alright, so what we're saying here is that we're just using the law of conservation of momentum here, right? So it's, yeah. Now I'm just gonna draw in, so this would be the first final velocity, right? Yes. Okay, so this is our first sort of calculation. But once we solve this, we'll find that, okay, we find this, let me just, okay, just give me 1 second. We find that, I'll just type it again. This first side all equals 33.3, right? So we find this is 24.3, this is 9, you add them, you get 33.3. That equals 3, I'll just write V1 prime plus 2 V2 prime, right? But that's you can't solve that any further, really. However, then we use our second formula, the wonderful formula for the coefficient of restitution. And that's where things really get interesting. Well, not really interesting, but that's where things start to work out. So we'd have, and that's this, okay. So V minus V equals, we have the we have the initial velocities here. So 8.1. All I'm doing is I'm plugging in the values for this. I'll draw in the primes and stuff in a second. Minus 4.5. I'm looking at the data up here. And so we're saying here V2 prime minus V1 prime equals V1 minus V2. V1 minus V2. So let's solve for, what did I solve? I solved for V2. You can solve for V1, but you know, I solved for V2. Okay, so then when you subtract 8.1 from 4, or when you subtract 4.5 from 8.1, you get 3.6, and it's that plus V. Okay, yeah, so V2 prime equals that plus V1 prime. So we have these two things, and what we find is when we substitute this in for this, we can get something interesting. So let's do that. Okay. So 33.3. So this is really just it's just algebra. This is, and it's not exactly, you know, the hardest algebra you'll see in your life. If that's, you know, if you find this hard, that might, well, it is application, so it's not like it's, you know, you have to know what you're doing, but you know, it's easy once you get the hang of it. So here's what we find: 33.3 equals 3 v1 prime plus 2 3.6 plus v1 prime, and I'll just, yes, that is what I got. Okay. So then we can just do some, actually I'll just draw here. So this is 7.2, and this is 2 v1 prime.